Hello everyone, welcome to our presentation. I am Salman Rahman and my other team members are Said Al Saab and Mizan Rahman. I'm going to present our 990B course project work. So our topic was design and analysis of hybrid power system for Rigolet Labrador, and our supervisor was Dr. Mohammad Tariq Iqbal. So here is our table of content, what we're going to discuss throughout all of our presentation, and what was our result, what was our findings and analysis. So let's start with a short introduction. So as we know, the demand of the sustainable energy is going increasing day by day, and most of them depends on the diesel generator to get the electricity. And for all that location, we need 835,000 liters of diesel per year, and which cause of reducing which cause an emission of 2,238 metric tons of carbon dioxide. And for that reason we plan to move to the hybrid power system, which will reduce the dependency of the diesel fuel, and then cuts the emission rates, and this is also cost effective. So here is the Canada's net zero target. Let's go to introduce and find the significance of why we need to convert to the hybrid system from this traditional system. So as per the Canada's net zero target, they have a motto like a healthy environment and a healthy economy. So for that purpose, they are going to limit their natural gas and coal emission by 2030, and also there will be uh, phase out by phase out by 2030 from the coal generation, and they're going to transition to the net zero electricity grid by 2035. And for that purpose they are going to expanding the renewable energy sources like the solar, wind and hydro biomass, and implementing the smart grid technology to optimize the energy flow and reduce the waste. And federal government and the provincial government also going to the partnership to clean energy projects and regulation, and also engaging the indigenous communities in renewable energy projects to supply them the energy from the renewable sources. And also they have planned to carbon pricing to ensure the shifting from the high emissions to the renewable energy sources. So here is our site map for the Rigolet. This is our location. The location was this is the location of the geometrical location, and then most of those areas are a lack of the road access, because as you can see from the map, our location is besides the seaside, so there is only one of the way to connecting the other province or city, the sea, and any kind of ferry or the ship. So this is the only one reliable transportation, and there as per to 2021 data, the population density was 5.27 kilometer square, and then the area was 5.27 kilometers square, and the population density 62 kilometers square, and the total population was 327. And their energy demand, this is the most important point for our project, that their daily energy demand is 8,129 kilowatt hour per day, and then peak demand is 706 and 74 kilowatt. So now we can see a small overview of their generation and consumption of electricity for the 3 years, 2029, 2022 and 2021. So as you can see, their main power source is fossil fuel, this is the diesel, and their service provider is Enel Hydro. And they have three sets of generator. All of those, the total capacity is 1,320 kilowatt. And their main transportation to get the fuel is ship, and then their fuel storage is 800 8,000 813,000 813,000 liters, and their annual fuel consumption is 835,000 liters per year. And this system was installed in 1998. And as I have mentioned in the earlier, that their annual consumption for the fuel is 835,000 liters, which leads to 2,238 metric tons of carbon dioxide emission annually. And as per their data, we can say that their monthly consumption of fuel is 71,000 liters per year, 70,000 liters per month, and then capacity already mentioned that 813,000 liters annually. So they are going to replace their system in 2030 because they have installed their system in 1998. So this is their lifetime is going to end. So this is the high time to convert their traditional system to the hybrid system, which will be a feasible solution to good potential harnessing potential from the energy and solar energy and the wind energy. So here is a site analysis for our location. Like this graph is showing the monthly solar index, and we can see we get the maximum energy output from solar in the month of April to August, because that time will be the summer season. And if we see this bar chart, this is the monthly wind speed. The average wind speed is showing 6.47 meter per second, and then the solar irradiance is 2.87 kilowatt hour per meter square per day. So we can see there is a fluctuation on the wind speed, like at the time of May to the August. But on that time, our solar output is a bit higher because of the summer season. So if when the wind power will be goes down, then our solar will be backup for the wind. So we can get the backup as well for our winter season. From the October to January, there is a rate of uh, lower rate of generation from the solar, but on that time there is a possibilities of high wind. So that's why we can get the our maximum output from the wind energy for the October to January or February this term. So this is our proposed design system from the Homer. We designed this system with a diesel generator, and then wind turbine, solar panel, and a inverter, and then battery system. So as per the suggestion of Homer, we are supposed to install 38 wind turbine. Each of these are 80 kilowatt, and then one inverter. And we also selected 340 watt of the solar panel, and we need the 2,535 panel all total. And for our storage system, we selected 12-volt battery, and then we need the 12,000 of the battery pack. And here is our result analysis for the monthly electric summary. As we can see, the first bar chart, there is the maximum portion is covered through the wind turbine, and the little bit of will be supported by supported by our solar system, and very less amount for the very less amount of the generation we have to use our diesel generator. That means we have to burn the less fuel. And we can see that 88% of the total energy comes from the wind turbine, and then 10% will come from our PV panels, and the rest of the rest of the percentage covered by the near about the 2% covered by the diesel generator. And here you can see our monthly use of diesel fuel. So you can see we have to the maximum use of our fuel will be in January and the December month, which is near about the 60 liter per hour, which is very less. And if we focus on the month April to September or August or October, then you can see it's very little, near about 20 liter per hour. And for the annually, it is drastically reduced for the hybrid system is 59,000 liters per year only. But without the hybrid system, we have to burn 835,000 liters of diesel fuel. So it is really cost effective in case of the fuel burning. And you can see there is an average output we need to get from the diesel generator. It's near about 60. Here you can see average is 60 liter per hour of diesel generator use. So by converting the hybrid system, we can save 1.64 million dollar per year. And in case of carbon dioxide emission, we can save the 14 times. We can reduce the amount of emission 14 times rather than the current situation. So here we can see the output of solar and wind power annually output. So first one is shows the solar power output. So from the solar we will get near about 1800 kilowatt, and then from the wind turbine we will get the constantly average like 2500 to 3000 kilowatt per year. And here is our total data output for the renewable output and the diesel generator. So here is our total renewable output data, and for the diesel generator, let's see we have to use only less than 200 kilowatt for the diesel generator. And here is our cost benefit analysis. Like for our total system, the NPC is 4 million, approximately $4 million. But we already mentioned that by converting to the hybrid system, we can save the fuel cost almost around 1.64 million per year. So by utilizing our 3 years of fuel cost, we can implement our own hybrid system for our that remote location to see how much we can save from the fuel, and it also reduce the carbon dioxide emission. And we also implemented our design through the MATLAB, and here is our some output from the MATLAB. So this is the wind voltage, wind current, and the power, and here you can see the PV power, PV voltage, and the PV current. So this part we can see the output of the diesel generator and our load forecasting. So now we are going to discuss about our implemented data lower system, which is actually a SCADA system. So we implemented a data lower system to collect and store all our data in the cloud system, and also monitor of the whole system cloudly. So here is a training system. It is a Festo solar and wind energy training system, which is available in our lab. So here you can see the demo wind turbine, and this is the solar panel. There is some load, and the system. This design setup. This is here. So this is the main setup we used for measuring the data from the solar and the wind system, and then by this Arduino we send all data through to our cloud system. So this is the Arduino. This is measure all the output of the solar and the wind. We use two sensors, like one is the voltage sensor, one is current sensor for wind, and this is the voltage sensor and current sensor for solar. So this is Arduino collected all the data from these sensors, and then send this data to the cloud through this Arduino ESP8266 Wi-Fi module. And now we can see our flowchart of the SCADA system, how our SCADA system or the Arduino controller system is going to work. So let's say this is our wind turbine connected to our one current sensor and one voltage sensor. This sensor is always collecting data, and then sending this data to the Arduino microcontroller for processing these things and send this to the cloud. And then the solar module also doing the same thing. The current sensor and the voltage sensor sensing the data from the solar module, and then implemented and then collected those things collect those data and sending to the Arduino microcontroller, and then the microcontroller collect and utilize all the data to send the microcontroller things the cloud. I forgot to mention that for this cloud system we are using an third-party open source cloud system. This is thing is the cloud, and we can access to this cloud system from our phone, laptop, or desktop from any part of the country, any part of the world. So yeah, so this is an demonstration of our uh, serial monitor of the Arduino, and then this is the physical multimeter. We have measured the voltage and compared to our serial monitor compared to our the implemented system design SCADA. So the serial multimeter shows that our voltage is 13.13, and then we recorded and we got this data from sensor is solar voltage 13.08, which is really very similar to our other physical data. We can say that our system is working accurately. So here is some interface of our system, cloud system. So we can visualize all the data through like this chart, and if we want, we can add more bar chart, or we can manipulate this system as much we can. We also can analyze our data through the MATLAB, and we also can import our data and many more options to visualization. And yeah, so this system is showing our location, and here we can also imported our video analysis. So in conclusion, I want to say that uh, as I mentioned that most of these isolated province or isolated states are depends on the diesel fuel, which is really alarming for the carbon dioxide emission. So by addressing those things, we can convert to the hybrid system. The hybrid system is really very sustainable and then reliable, and also the eco-friendly. And already I have showed the cost benefit analysis, like by saving utilizing the 3 years of fuel cost, we can implement a proper hybrid system on our remote location. And we can, and if we can successfully implement the system on a remote location, so this will be the model for other small or isolated communities, which will that will inspired by seeing our project. And at the end, we have to say that implementing those things, we can achieve the net zero goal as early as possible, because the current 2050 goal is achieving the net zero goals. So that is everything for our project, and then here is the references, and I am going to show a small video clip of our project. I'm going to play this video clip. So this is our total system. Here I am to say this is the sensors, current sensors and voltage sensor. This sensor is for solar, and here is two Arduino. This is for the Wi-Fi module. This is Arduino Uno measuring all the data. Yeah. And then sending those data to the ESP, this Arduino Wi-Fi module, and then we send it to the cloud. This is our the whole training system, solar panel, and the wind turbine, let's say. And by this controller, we can control the speed of the wind turbine. By controlling the wind turbine speed, we can increase and decrease the output. Like here you can see the calibration of the meter. This meter is for the solar system. So this is our physical meter. We are measuring the data, and then here we can see the output in our serial monitor. This is 13.221 we are getting from our solar system, and see here we also are getting almost the accurate data. And yeah, this is our cloud system. Yeah, this is very interactive, and we added the we added the location there and some meter gauges, and then this is an icon by which we can confirm that our system is working or not, or it is running or stopped. Yeah, there's this small demonstration of this small video clip of our implemented system. So that's all from our project. And if any question, you can ask. So thank you everyone for joining.